Hello. In this lesson, we're going to take a look at the Y to Delta connected three-phase circuit. And as you'll hopefully see, not as you can see, but as you hopefully will see, it's basically exactly the same as the Y-connected circuit as far as how the analysis goes. We'll draw out the whole circuit. We're still going to use that A-phase equivalent circuit, solve for each of the different parameters in that circuit, and then just do the minus 120 degrees for the B phase and the plus 120 degrees for the C phase. When we calculate our voltages and currents on the load terminals themselves, you'll see they're slightly different than they were for the Y-connected circuit, but overall the processes are exactly the same, just a slightly different equation that you need to have memorized. So let's go ahead and get on into it. All right, so just like the Y circuit, the sort of hardest part of taking a look at our Y-delta circuit is just drawing it out. So let's go ahead and take some time and do that. Like before, we've got three sources connected in that Y configuration to a common node. We'll call this guy VG for generator, comma A. We'll call this guy VG, comma B, and VG, comma C. And just like before, each source has an impedance. We'll call that Z little a and Z little b and Z little c. And then we have a node little a, and then the transmission line. Let's change colors. Actually, first, and a node little b, and a node little c. Then a transmission line with an impedance ZLA, ZLB, and ZL, comma C. And then we'll connect that to a node, call that capital A, capital B, and capital C. Now here's where it diverges. Now we've got a delta connected load. So the way that's going to look is like this. There's a line that connects A to B that has impedance Z delta. There's a line that connects B to C with impedance Z delta. And then there's a line that connects C to A, also with impedance Z delta. So there we go. It's set up like this. Let's go ahead and figure out some of our parameters. Just like before, we have a current on each of the lines, a line current. That's IAA, IB, comma, capital B, IC, comma, capital C. But then we also have a current flowing down from the A node to the B node. We'll call this IAB. Current flowing, we'll call it IBC. And then current ICA. We'll also label, let's see, let me use L for that. A voltage, we'll call this VAB. And then a voltage drop, VBC. And then a voltage, notice it's flipped over, VCA. Just like that. Now, we can characterize it in much of the same way, in fact, exactly the same way that we did the Y circuit by creating that single phase equivalent circuit. And just like before, we'll build it off of the A phase, since that's our 0 degree point. Now, the diagram for the single phase equivalent circuit is exactly the same. So we'll have our voltage source VG, comma A, that source impedance, Z sub little a, the node A, the transmission line impedance, ZL, comma, little a, the node capital A, and then we'll have an impedance ZA, and everything will loop back around. Now the catch here is, well, what is ZA? Turns out there's a very simple equation for calculating that. ZA is just equal to that Z delta divided by 3. So we'll use that in our example. And then we've got the rest of our parameters here. We've got our I, our line current, IAA. We've got a voltage. Let's see. V little a. We've got a voltage drop V, capital A. And we'll use all of these to characterize our other parameters for the entire circuit. Remember, we calculate for phase A, and then we just subtract 120 degrees for B and add 120 degrees for C. So let's go ahead and work an example. So we've got a Y-connected generator, or specifically a Y-connected positive sequence generator. It's actually the same one from the example in the last lecture. It's got, let's use blue, a VG, which is equal to 120 degrees, or excuse me, 120 at 0 degrees volts per phase. And it has an impedance 0.2 plus J 0.5 ohms per phase. The transmission line has an impedance, we'll call that ZL, equal to 0.3 plus J 0.9 ohms per phase. And we have a delta connected load with Z sub delta is equal to 118.5 plus J 85.8 ohms per phase. Now in part A, we're going to go ahead and have, or construct, the A phase equivalent circuit. So we've already got everything we need to do that. We've got our generator that's at 120 and 0 degrees volts. Then we've got that source impedance, which was 0.2 ohms in series with plus J 0.5 ohms. There's our little a. Then we have a line impedance of 0.3 ohms connected in series to positive J 0.9 ohms. No capital A. And then we have a load impedance. Now here's where we have to do the divide by 3 business. So let me go ahead and just finish drawing this. Remember that our Z sub A is equal to Z delta divided by 3, which means it's equal to 118.5 plus J 85.8 39.8 ohms divided by 3, which gives us 39.5 plus J 28.6 ohms. So up here, 39.5 ohms and J 28.6 ohms. And there is our equivalent circuit. Next up, part B wants us to calculate the line currents. So that's our IA, A, IA, B, and IA. Wait, what am I doing? Not A, B. That's coming up. IB, B, and I C, C. And our current flowing around this loop is our IA, A. So if we go and look at our equivalent circuit, we know that the current is just going to be our voltage divided by all of this impedance. So it's just going to be IA, A is equal to VG, A over Z little a plus ZL, A plus Z of capital A. Now we've got everything we need, and we can plug all the parameters in. IA, A is equal to 120 over, let's see, Z little a was 0.2 plus J 0.5 plus the line impedance 0.3 plus J 0.9 plus the load impedance 39.5 plus J 28.6. So I'll leave it up to you to do that algebra, but if you do that, you'll get an IA, A equal to 1.92 minus J 1.44 amps, or as a phasor, 2.4 at minus 36.9 degrees amps. And to do the B line current, B, B, is just going to be this, minus 36.9 degrees, minus 120 degrees. So that's going to get us 2.4 at an angle of minus 156.9 degrees amps. And for C, C, it's going to be 2.4 at an angle of minus 36.9 plus 120 degrees gets us 83.1 degrees amps. So that's it for part A. That's how we calculate our line currents. Part C asks us to calculate the phase voltage at the load terminals. That's going to be our VAB, VBC, and VCA. Remember, from our diagram at the very top, that's these voltages across each of the delta connected load phases. So the equation for VAB, which we'll use to get the rest of them, is pretty simple, but it's got this thing. You might remember it from the last lecture. So it's square root of 3 at an angle of 30 degrees times VA. And remember, VA is just going to be the voltage drop across our load. So real quick, first, let's go ahead and figure out what this square root of 30 degrees is as in rectangular form. If you solve it, you get 1.5 plus j 0.9. Now, if you watched the previous video or are following along in the textbook, this is like 0.87. Just to keep things simple, I rounded up to 0.9. But that means our final answer is going to diverge from the textbook solution just a hair. Don't let that freak you out. We're still doing everything correctly. So, let's see. VAB, we can write our whole expression for VAB. That's going to be 1.5 plus j 0.9 times IA, comma A, times Z, capital A. So now we're ready to write out our big monster expression. Don't need a keyboard for that. VAB is equal to 1.5 plus j 0.9 times 1.92 minus j 1.44 times 39.5 plus j 28.6. And after a fair amount of algebra needed to solve that particular problem, you're going to get that VAB is equal to 177.34 plus j 102.33, or as a phasor, 204 at an angle of 30 degrees. It was like 29.89. I just rounded it up to 30 degrees. So that's that. That means that our VBC is just going to be 204 at an angle of 30 degrees minus 120 degrees gets us minus 90 degrees. And our VCA is equal to 204 at 30 degrees plus 120 degrees gets us 150 degrees volts. And there we go. There's our phase voltages, the voltages on each of the loads. Part D, the last part we're going to do, wants us to calculate the phase currents. At the load. That is our IAB, IBC, and ICA. So the equation for IAB is actually equal to this. It's a little bit different. It's 1 over the square root of 3 at an angle of 30 degrees times just IA, comma A. And I've figured out 1 over square root of 3 at an angle of 30 degrees. Again, I played it kind of fast and loose with the rounding, but I got 0.5 plus j 0.3. So let's drop everything in. IAB is equal to 0.5 plus j 0.3 times 1.92 minus j 1.44. And that's going to get you a final answer. IAB equals 1.392 minus j 0.144. Or as a phasor, that's going to be 1.4 at an angle of minus 5.9 degrees. And that's in amps. And from that, we can easily calculate IBC as 1.4 at an angle of minus 5.9 negative 5.9 minus 120 is minus 125.9 degrees. And ICA is equal to 1.4 at an angle of negative 5.9 degrees plus 120 gets us 150 and 14.1 degrees. And that is in amps. So there we go. There's our characteristics for this delta connected load. We figured out the voltages across each phase of the load and the currents. So that was the Wye-Delta connected circuit. Hopefully you saw it's very similar to the wye-connected circuit as far as how the analysis is performed. We just have to tweak those equations just a little bit to get the voltages and currents at each of the phases of the loads. So in the next lesson, we're going to talk about doing power calculations with our three-phase circuits, and that'll be it for our discussion of three-phase circuits in Chapter 11. We'll move on to something totally new after that. So as always, if you have any questions, comments, or concerns, please let me know. And if not, I'll see you guys in the next lesson.